everybody. It's really hard to talk about chemistry without talking about energy changes that happen during chemistry. So while chemical reactions take place, we usually will see some type of energy change that goes along with it. So there's never a bad time to talk about current issues and global issues with chemistry. So I'm going to do that first, and then we'll take a look at some of the finer points of energy basics. So in this picture here, we can see that we have an oil drum. It seems to be squishing planet Earth. And I'm guessing that the reason why whoever created that image did was to show that fossil fuel use is not really that great for planet Earth. Not only do you risk spills like we see all the time, month to month around the globe, but we also see spills in our backyard, such as the Gulf of Mexico, such as Alaska. We had some very large oil spills there that wreaked havoc on the environment. The second issue that goes with using fossil fuels for energy, of course, is when we burn them, their gases go up into the atmosphere, and CO2, the big one that we're concerned with, its addition to the atmosphere increases climate change. Many experiments have been done where CO2 when it accumulates in a trapped area, the heat will increase in that trapped area. There are climate scientists who work on these studies every single day, and all seem to come to the same conclusion, that human-based carbon dioxide production is changing the climate. We can also look at alternatives to using fossil fuels, alternatives that are much safer for our planet as well, such as wind energy. There's many places around our country and the world that have continuous wind all the time. Why not harness that and use that as an alternative to a fossil fuel? Okay, I tell my students, what's the difference between, when you spill oil, it's a really big mess, but if you were to spill a windmill, all you're going to make is either a really big splash or a really loud bang when it hits the ground. So there's a big difference there in energy production, how one is renewable and one's non-renewable. Of course, the fossil fuel is a non-renewable resource because it takes so many millions of years for it to accumulate under the ground, either in coal or with our oil drum there and petroleum. But with wind, it's renewable because it's always there. There's always those windy areas that it just seems that the wind is always blowing, so that it would be considered a renewable energy resource. Also, solar. We have plenty of areas in our United States where we have non-stop sun and very little rain. Those would be great areas to produce a lot of energy for localities in the United States. One recent fact I looked up was that Germany has recently agreed to, and I think they have accomplished, 50% of their country's energy now comes from solar energy. They're weaning off of nuclear energy after seeing the Fukushima disaster and other nuclear meltdowns as well. It's just too dangerous for too small of a country. So they are looking to alternative energies to compensate for not burning those fossil fuels anymore. And then, of course, we can take a look at things we can do at home, such as using a CFL, which uses just a fraction of the energy, fraction of the electricity that a normal light bulb uses. We can also take a look at nuclear. But nuclear, as great as it is, as much energy as it produces, has inherent dangers involved with its use. It just takes one big tsunami or one mechanical malfunction and you can destroy an entire area. And we've seen that happen. So there is an inherent danger that comes with nuclear power as well. And then lastly, another renewable resource we have are plants. Plants can actually be chemically changed into ethanol. If maybe one of your vehicles is E85 capable, that means that it can run on fuel that has come from plant matter. Okay. Now, they've done some research with it and they found that the corn ethanol wasn't exactly as great as we thought it might be, but now they're doing research with microorganisms and they're feeding these microorganisms sugar, they're messing with their genetics a little bit, and these organisms are starting to produce diesel, which we call biodiesel now. So there's always new experiments being done, and we're looking towards the future to get it off of fossil fuels and getting onto these alternative energies that are non-polluting and they're renewable. All right, let's get on to energy. So with energy, it has a definition. It's defined as the ability to do work or produce heat. Either one will work. And probably when you were in middle school, you learned about two types of energy. The most common that are talked about in middle school are potential and kinetic energy. Potential energy, as you can see, is energy due to composition or position. So when we say composition, especially as we relate it to chemistry, we're talking about what our particular chemical is made of. When we talk about position, if we go back to our middle school example, we're talking about that rock, that round rock that sits on top of a hill. And while it sits there, it has all this potential energy, and it takes a nudge to get it rolling, and that potential energy will turn to kinetic energy as it rolls down the hill. But we can also use position in chemistry a little bit if we start looking at molecules and see how the atoms and elements are positioned within the particular chemical. With kinetics, not only do we use this for like the physical sciences and astronomy, but we can also look at it in terms of chemistry as well. If we talk about gas chemistry, you guys learned that the little particles are constantly moving around in random straight line motion until they hit something, and then they bounce off at a deflected angle. They have a new straight line that they travel in until they hit another particle or a wall and they bounce off. So there is kinetic energy in matter as well. Even solids vibrate. Solids that are at room temperature. The little atoms are vibrating back and forth, up and down, diagonally, every which direction, and they bump into neighbors sitting next to them. So kinetic energy then is related to constant random motion of particles. Temperature is directly proportional to Ke, to kinetic energy. Why? Well, let's talk about Ke just for a second. Ke is kinetic energy. It has a formula 1/2 mv squared. Now, the V is not volume, the V is velocity. And we've learned that as you heat things up, things move faster. So as the velocity goes up here, we get a direct increase as well in kinetic energy to match. So we can say it's a directly proportional relationship. Potential energy in chemistry, let's take a closer look at that, really relies on three things. What type of atoms are involved with your particular chemical reaction? There's some atoms of elements on our periodic table that we learned that they're not too reactive. They're not interested in bumping into and bonding with other chemicals. For example, our noble gases, they were all stable and content because they've had full outer electron shells. Type of bonds a chemical has or forms. Single bonds tend to be a little bit lower energy. Double bonds a little bit more, and triple bonds a lot more energy can be stored when you have a triple bond between two elements. There's one, for example, called acetylene. Acetylene's formula is C2H2. These two C's have a triple bond between the two of them, and that triple bond, when it breaks, releases a lot of energy. And there's the particular arrangement of atoms. There's stability in some arrangements, and there's instability in others. If your arrangement of atoms in a molecule are very unstable, they have the potential to have a lot of energy in them. Let's look at some examples and address whether we're talking about kinetic or potential energy. For example, a Justin Verlander 100-mile-an-hour fastball, we know that's moving, so that would definitely be kinetic. So I have A up there, I'm just going to write K for kinetic. A triple bond in C2H2, we just talked about this one. There's the triple bond, here it is as lines going across. This one has a lot of stored energy, this would be potential. Structure of glucose. Here's glucose, an atomic structure, a ball and stick model of it. And in this case here, the structure itself has potential energy in it because of the way that it's formed. And last year in biology, you learned that as this breaks down, as each cell takes this thing in right here, it's going to turn it into ATP. And ATP is going to fuel me and you in whatever daily activities we have to get through. Just thinking and listening is going to take ATP to happen, and that's currently being used. And then also helium gas particle. So I'm going to make this potential as well. A helium gas particle at 25 degrees, which is around room temperature. Of course, that's going to be moving. Gases are always on the move unless they're at absolute zero. So that would be kinetic energy. Okay, pretty easy examples, but essential to understanding how the two of those work. Let's talk about the law of conservation of energy. In the start of the year, we talked about the law of conservation of matter quite a bit, saying matter cannot be created nor destroyed. Well, we could say the same thing about energy. You know, I can't just right now work up a fireball and throw it at the camera. Why not? Because I don't have anything to produce that. But if I was in the classroom and I had some soapy water, I had my gas spigot that pumps out natural gas, I could actually do that. I could get a handful of something, light it on fire, and throw it at the camera, and it would be pretty awesome. However, it took chemicals and it took some supplies in order to do so. So I can't do that out of nothing. It's done in the movies all the time, but I haven't seen that power in real life yet. So energy can be converted from one form to another, but neither created nor destroyed. Okay, so let's talk about that for a second. Let's look at an ice cream cone. Let's say you go have yourself a nice, delicious ice cream cone. This happens to be full of sugar inside of it. And because there's sugar in here, we just mentioned that your cells convert sugars to ATP. Your muscle fibers will then use the ATP to help give you the physical strength to put yourself in motion, in this case on the bike. And so in this case here, we transform from a chemical energy to a different type of chemical energy, and then to a mechanical energy as well. So we see energy conversions start at one place, convert to something else, and that's the basis for what we're talking about here. Here we have solar energy, and solar energy is going to act as a catalyst for a process that happens in plants. We learned that last year as well. That's photosynthesis. And what's going to happen are the two inputs of photosynthesis, which are CO2 and water, are going to be helped by that solar energy. It's going to excite some electrons in these leaves, and through that process it's going to produce O2, and it's going to produce sugars. So again, we're going from solar energy to a stored potential energy in the tissues of the plant, and then if we ate that plant, we could again convert the chemical energy into mechanical energy with our muscles, and then into movement again. So again, multiple conversions exist here, but we always start somewhere. Chemical energy in the form of gasoline. Gasoline is a volatile liquid that turns into a gas very readily. Your car uses an internal combustion engine to use the reaction type of combustion to move pistons, and those pistons are coupled with other mechanical machinery that's going to allow your car to then mechanically move forward, and you go from potential energy in the gasoline to kinetic energy on the road. And the last example here, electrical energy. Electrons are going to go up the metal wire. They're going to come out these prongs here, and they're going to be converted to thermal energy in the case of this oven. So multiple examples of energy conversions from one source to another. We never create it out of thin air, nor do we ever destroy it into nothingness. So we can always track it. And what we're going to call this is the first law of thermodynamics. Those of you who take a physics course or even a higher level chemistry course, you'll learn about these laws of thermodynamics. And thermodynamics is basically the study of heat. So, you know, one branch of chemistry that's out there is called thermochemistry, the study of transfers of energy as heat that accompany chemical reactions and physical changes. So let's take a closer look at heat. So here I got my flaming jalapeno pepper, and we know that if this was on fire and you held your hands up to it, we would feel heat coming off of it. It would be considered an exothermic reaction. In science, we tend to think of heat a little bit differently than how we do just commonly. And what I mean by that is, if you think about cold, we think about cold spreading sometimes. I don't want to sit on something because it's cold, or this room is getting cold. But really, if we look at the scientific way of mentioning it and the definition behind it, we say that heat is the energy that flows from a warmer object to a cooler object when the two are in contact with each other. in these formulas that we'll see in this topic of energy, we're going to represent heat with the letter Q. But the important thing here is that understanding that if two objects are in contact with each other, the heat flows from the warmer one to the cooler one. So if you check out this picture down here, you can see that someone is holding a bunch of ice cubes. Now, of course, the heat is going to be transferred at this time from the hand into the ice cubes. Okay? We usually don't talk scientifically saying, well, the cold is being transferred into the hands. Now, we perceive the cold because we have little receptors underneath our skin surface that do that. But for energy's sake and for heat's sake right now, we'll say that these two objects in contact with each other, the heat is leaving the 98.6 degree hand and it's going in the 32 degree ice. So if we could measure it, this would be the hand temp. This obviously we don't have units on here. This would be the ice temp. And these two will stay in contact. If I was to hold my hands really tight, I could probably melt all of the ice over time. And eventually, the two might come reasonably close in terms of an equilibrium. So the water might eventually reach the same temperature of my hand. There's some other factors that are in play, like evaporative cooling and wind and other things, the ambient room temperature. But the two things in contact will basically come to an equilibrium with one another. What we could say to summarize then is when an object loses heat, its temperature decreases. When an object gains heat, its temperature will increase. So again, heat is the main focus here of our points. Now let's get into a little bit of terminology and then use that in some energy-related, real common basic problems that we see in Chem 1. The amount of heat required to raise 1 gram of water 1 degree Celsius is called the calorie. Now, we know the word calorie. We know that it's on food wrappers and labels. We're interested in calories because we want to know for our health how much energy a certain food will provide. Often it's a lot more than we use, but this one right here is not exactly that type of energy we're talking about. This one here, this particular type of calorie, is a bit smaller than the one you're thinking of. It's not the one on the food label. This one here raises 1 gram of water 1 degree Celsius. So I want you to think of like a cube of sugar. Okay, a cube of sugar is a really small thing. And imagine that this was full of water. Okay, so your cube of sugar's no longer sugar, but instead it's just a cube of water. This cube of water would require a certain amount of energy to raise it 1 degree Celsius. It probably wouldn't be a whole lot of energy because, that's a pretty small quantity of water and 1 degree is a pretty small increase. But if we take that idea of the calorie one step further, if you have 1,000 of these, you then have a capital C calorie. Now, this is the one we do find on our food labels. This is the one that we're concerned with here. So 1,000 of these little ones, 1,000 of these ones that raise one sample of water 1 degree Celsius, that's 1 calorie. If you think of yourself and imagine how many of these would make up one of you, since you're so full of water, you can understand it takes a lot of calories to keep that amount of liquid warmed at 98.6 degrees for 80 years of your life. It's going to require a lot of meals and a lot of calories. There's also a really important relationship between those little c calories and energy, and it's 1 calorie equals 4.184 joules. You see that down here. I think both of those are really notable because they allow you to do a lot of problems like the one we're going to see now. Okay, so a common thing that has to be done in Chem 1 is the conversion of energy units. And down here, you can see I have a table. And I put more commonly used relationships in energy and thermodynamics and the chemistry of energy. And you can see like 1 joule equals 0.2390 cals. So if you're using it in the problem, you'd set up a unit factor type of a conversion factor, a ratio. So we'd have 1J over 0.2390 cals. Or maybe you need it the other way because you are starting with joules. So in that case, you'd have 0.2390 cals over 1 joule. Okay, both of them work. It's depending on what you need, which one you'll decide to use on that. 1 cal and 4.184 joules. Okay, or you could do the reverse. You could take that one down and that one up over a line as well. Here's another one like that. Here's another one like that. Know that you can convert from one to the other very, very easily using a conversion factor, a ratio of how one thing relates to another. Okay, so just know that going into solving problems with chemistry and energy. All right, let's look at a real simple example. A Pop-Tart has 310 calories, big C, per tart. You eat it. How many little c calories have you just eaten? So if you have 310 big C calories, on the previous page we said that a big C calorie, one big C calorie, was equal to 1,000 of those little ones. So 1,000 little C cals is equal to one big C calorie. So what that allows us to do then is we can cross cancel units that are above and below like that. And we have a simple math problem, 310 times 1,000, which of course is 310,000 little c calories. And if your teacher is a stickler about scientific notation, you would have 3.1 times 10 to the 5th power little c calories. All right, let's look at another example. An exothermic reaction releases 86.5 kilojoules. How many kilocalories of energy are released? Now, this one here might take a little bit more work. There's a bit more to convert in this one because there's no direct relationship on our little board here, on our table, that goes from kilojoules to kilocalories. So here's how you would do something like that. We'd start off with our given, 86.5 kilojoules. And from here, we would probably convert to joules first. We see that there is a joule to cal relationship, so let's get there. And what we could do then is say 1 kilojoule, a kilo of anything is 1,000, so we have 1,000 joules, and that allows us to do this and this. We can then, because we're now in joules, convert from joules to cals. And here we have 1 joule, which I'm going to put on the bottom, is equivalent to 0.2390 little c cals. That allows me to cross off my joules. And I'm not quite yet in kilocalories, but I can get there real quick because 1,000 little c calories equals 1 kilocalorie. So then I can use that for my last conversion, and I'll go like this. 1,000 little c cals is the equivalent to 1 kcal. So now what I'm going to do is solve at this point because the only unit that's left now is this one here, kcal, exactly what you're being asked. Now, how do you solve something like this? Well, we've done a few of these in class before. We're going to take everything on top of this line here, multiply it together, hit enter if you want, and then we're going to divide it by all this stuff down here, multiplied together. Okay, so let's do that right now. Go ahead and pause it, see if you can come up with the right answer, and then unpause it when you're done calculating. Okay, I just finished calculating myself, and I got 20.6735. So my answer looks like this, 20.6735. It would be kcals. Now, again, you may have a teacher who wants this stuff in scientific notation and sig figs. If that was the case, we'd take our given. It has 3 sig figs, and we report that as an answer. So it'd be 2.07, because there's a 7 behind the 6, times 10 to the 1st power kcals. So there's a lot more to come in talking about energy and chemistry. This is just kind of a very brief opening. So keep your eye out for more videos. I hope this helped you understand the basics of energy and chemistry. Keep reading that book. I'll see you next time.